zeros of polynomial functions. There's a lot here. There is a lot here. Okay, I really don't see us getting through all of this today, but the stuff that is here is important. There's a ton of stuff about computing the zeros of a polynomial. Now, one of the things to be mindful of is what does it mean to be a zero of a polynomial? That's a place where if you take that number and you plug it in, the polynomial has a value of 0. So for example, one polynomial might be something like x squared minus 16. The zeros that are real, and when it says real, it means that are real numbers as compared to complex numbers. Oh yeah, remember those? We did those a while ago, didn't we? Section 3.3 or thereabouts. Okay, the zeros for this would be x equals -4 or a +4. Well, gosh, how would we know those are zeros? If you take the -4 and you substitute it in there, -4 squared is what? 16. Subtract 16, you get 0. +4, substituted in there. 4 squared is 16. Subtract 16, boom, 0. So does that bring back to memory what a zero of a polynomial is? Okay? That's all there is to it. It can get messier. It can be something like, let's say x squared minus 5x plus 6, and would suggest that, well, try 2 or 3. Well, let's throw 2 in there. 2 squared is 4. Minus 5 times 2. Well, 4 minus 10 is -6. Plus 6 is 0. 2 is a 0 of it. Throw 3 in there. 3 squared is 9. Minus, so we have 9 minus 5 times 3. That's 9 minus 15 is -6. Then -6 plus 6 is, okay? So anytime you have a 0, what that is going to do is it's going to be a value that causes this to return a value of 0. That's what it means by a 0. When you graph a function, if you have a graph that goes like this, the zeros are going to be these places where it intersects the x-axis. Now let's think about that and see if that makes sense. If it hits the x-axis, what is the y value? 0, isn't it? And remember, in each case, these functions are y equals something or other. Y equals the x squared minus 5x plus 6. When you plug in 2, the y value that comes out is 0. So these zeros of a polynomial function are going to be the values of x where the function either touches or crosses the x-axis. It can do either. In that example, it crosses. Here's an example where it just touches it. Whoops, disappeared on us pretty quickly. There it is. That makes sense to everybody where we're headed? Okay. We've got a long list of things to get done. We have to understand the factor theorem. Factoring higher degree polynomials completely. That means we're going to start looking at stuff like, x to the 4th minus 3. Let's try that again. X to the 4th minus 3x cubed plus 8x squared minus 9x plus 4, and come up with strategies for factoring that completely and figuring out what the zeros are. Okay? Oh, that's his third one. It says analyze polynomials having multiple zeros. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. understand the rational zeros test and Descartes' rule of sign. Descartes, what's a Descartes? That was a mathematician, lived back several hundred years ago, came up with some pretty cool ideas, and we're going to get to see one of them here. And the last thing we're going to do, we've already talked some about higher degree polynomials. If you can factor them, you can solve them. And the last thing we're going to do is something that's pretty cool, but it's really easy once you have it explained. It's the intermediate value theorem. It sounds awful, but the name describes what it really is. What does intermediate mean? Please? I just didn't hear you.
Oh, it's something like in between, like beginner and advanced.
Yeah, in between beginning and advanced. Okay, with Daniel's hockey gear comes junior is the smallest, intermediate's what he's out of, and then senior is the adult sizes. Intermediate's in the middle. Yeah, it's in between. Okay, so this is the value that is in between. Are you ready to hear an explanation of the intermediate value theorem real quick? Daniel used to be 21 inches long. Now Daniel is 72 inches long, 6 foot. Is it true that at some point Daniel was 50 inches tall? If he started out 21 inches long, he's now 72 inches long. At some point, was he, let's say 60 inches tall? Did he have to be 60 inches tall at some point? Had to, didn't he? Because when you grow, you just don't walk around like this and, whoa, did you see that? That's not the way people grow, is it? Okay, it's a smooth, continuous process. And you hit every height in between, don't you? There you have it. That's the intermediate value theorem. If you've got a low number and a high number, you'll achieve every value in between the low and the high number on a continuous function. That's it. Wow, the intermediate value theorem was pretty easy. Hopefully it was a little silly for you too. Okay. You're given some polynomial. Let's say we have something like x squared minus 5x plus 6. Okay, so we have this function, f of x equals x squared minus 5x plus 6. And you're asked, is x minus 3 a factor? Well, there are several ways to figure out if x minus 3 is a factor. One is to do synthetic division. We can do synthetic division because we'd be divided by x minus 3, wouldn't we? The number that we would set it up for the division would be would be 3, and then we would do our 1, our negative 5, and our 6. And is that looking familiar on how to set that up? So one way would be synthetic division. A second way would just be plain old long division. Either way would work fine. Another way that's sometimes quicker is it is a factor if what? F of k equals 0. Yeah, well that's fine, Chuck, but I don't know what that even means. What this means x is going to equal 3, doesn't it? You buy that? If we evaluate the function at 3, we're going to get 3 squared minus 5 times 3 plus 6 equals. What's that equal? It's 0. If it equals 0, then what we started out with, x minus 3, is a factor. It's a quick, easy way to test it. You just plug it in and see what you get. Yeah. So if you get back 0, it's a factor. What if you don't get back 0? Does that mean you're bad and you're awful and you've done something wrong and there's the door, use it? No, it just means it's not a factor. That's all the more there is to it. It's not a factor. Okay? So there is that. To check to see if something is a factor, just plug it in. Now the thing that will mess people up is if they're given a factor like x minus 3, they will try substituting in a negative 3. That will not work because that is not the value of x that you're being given, is it? That is not right. It needs to be the function evaluated at positive 3. Be careful to always take the negative. So if you had a factor like x plus 4, you would evaluate the function at what value? Negative 4. If it equals 0, you've got a factor. If it doesn't equal 0, it's okay. It just didn't work, which is fine.
What case will it equal 0 though?
Well, here. Let's take our x squared minus 5x plus 6. And then let's say is x minus 1 a factor? This would be a real easy question, hopefully, for Friday's quiz. Is x minus 1 a factor? Well, what would k equal? 1. So let's try it. We've got 1 squared minus 5 times 1 plus 6. 1 minus 5 is a negative 4, isn't it? So this is going to give us a negative 4. Negative 4 plus 6 is 2. Is it a factor? Nope. It's just that simple. Nope, it didn't work. Nobody hates you or anything like that. Okay? There have been times I've submitted proposals before either the department or the faculty here, just ideas. Sometimes they say yes, sometimes they say no. If they say no, does that mean they hate me? No, it just means that's not an idea we're interested in. That's all it means. It's nothing personal. Same thing here. It just means that is not going to work as a factor with this polynomial. That's all it means. So it's just as safe to say no as yes. Okay? All right. So let's see. Use the graph in the factor theorem. I'm not sure where the graph went. Where'd it go? Graph got lost somewhere. Here we go. Here are a couple of graphs that we can take a look at. On the graph to the left, you're given the function x squared minus 2x plus 3. There's that function. And then you're asked to identify what the factors would be. Now the factors, or let's first go with the zeros. The zeros are going to be where the function intersects the x-axis. Because when it intersects the x-axis, the y value is 0. Okay? So you're going to have a 0 here at negative 1. And you're going to have a 0 here at positive 3. Okay, you get 2 zeros. The thing to be careful of is if x equals negative 1 is a 0. Now watch the terminology. If this is a 0, a factor is x plus 1 when you've moved the constant to the other side. Don't get your factors and your zeros mixed up. It's easy to do. thinking about this, that, or the other thing in the problem and can get it mixed up. Okay, take a look at this function. What's the zero of this function? You got to be careful. A zero is where the graph intersects what? X-axis. But Chuck, you circled the y-axis. I know, I was trying to check you to see if you're just going to grab every place that it intersects an axis. And the answer is no, you don't. You only want where it intersects the x-axis. In this case, it would be x equals, trying to read that, looks like it might be 1. Does that make sense? Now, if x equals 1 is a 0, a factor would be x minus 1. Yeah. The factor would be x minus 1. Right, because you've got x equals 1, so to get a factor, you move it to the other side. Whoops, if I move it to the other side, I'm going to get a negative 1, and oh, this is going to be equal to 0, which is what makes that a factor, isn't it? Is everybody good? All right. It is possible for a 0 or a factor to occur more than once. For example, suppose I cook up a function where it's x minus 3 to the 5th power, x plus 7 cubed, x plus 1, and we'll just call it quits with that. We could write that thing out, and if we wrote it out, it would be x minus 3 times itself how many times? 5 of them. This is termed to be a multiplicity of 5. Does that make sense? The x plus 7 is a factor with a multiplicity of what? 3. And then the x plus 1 has a multiplicity of 1. In this case, each of them has an odd multiplicity. It's possible something could have an even multiplicity. For example, let's take this x plus 1 and square it. Knowing what the multiplicity is helps you to better understand how the function is going to behave at that location. If you have an odd multiplicity, okay, if you have an odd multiplicity, which is these two, the graph crosses the function. Now, it doesn't tell you what the multiplicity is. Or I'm sorry, the graph crosses the axis. I think I said the function. If it's an odd power, it crosses. If it's an even power, it'll come up to it, but it won't cross it. So you can tell by the multiplicity how the graph will behave at that 0 on the x-axis. Will it cross, or will it just turn around and go back where it came from? Does that make sense to everybody? So one of the things that I could do on a quiz, test, or whatever is to draw something like this and say, okay, you've got some zeros. Let's say this one is odd, even, odd. say that the lead coefficient is greater than 0. Sketch a possible graph that would fulfill those various criteria. It has an odd, then an even, then an odd multiplicity, and the leading coefficient is greater than 0. Well, what's the leading coefficient greater than 0 going to tell you about the graph? It's going to be going up, right? Okay. Odd means it crosses or just touches and turns away? It crosses. So it come up. Let's see. Here it's going to touch and turn away. And there it's going to go. Oh. And that's it. Kelly, you look kind of shocked. I guess this depends. Let's see here. If we have something odd, so this is going to be something like x cubed, x squared, x. So it's going to give us a total power that is even. So it's going to be an even function. X to the 6th power. Okay, an even degree. Now with an even degree, if the leading coefficient is positive, so let's take something like this. Y equals x squared plus 2. Is that even degree? Is the leading coefficient positive? Okay. Where are the legs or the tail's going to be going? Up. Yeah. So we do something like that. Thank you. Yeah. Does that make sense? Is everybody okay? Are even. Yeah. And the way to a way to think about this is if it's an even power, so you're going to get something like x to the 6th is your highest power. When you start picking more and more negative values like negative 84, and you raise that to the 6th power, is that going to give you a positive or a negative value back? It'll be positive. So the y value is going to be positive there. Slap happy and put it the wrong direction. Way to go. Does this make sense? Everybody good? Okay. All right. If you have a polynomial of degree n, okay, and it has n real zeros. It won't always have n real zeros. You might have one factor being x minus I, another factor being x plus I, and another factor being x plus 7. And if you multiply that out, that will give you a polynomial with normal integer coefficients. But if all of the zeros are real numbers, then you can break it up where you factor out whatever this lead coefficient is, and you multiply times each of the zeros. And it can be broken up like that all the way. So you can take some polynomial and break it up into something like a series of smaller pieces all multiplied together. Does that make sense? Okay. Here's one. Wish it wouldn't have shown the bottom part so fast. Write the complete factorization of 7x cubed minus 21x squared minus 7x plus 21. Okay. Oh, look, we're given zeros. Well, that was generous. -1, 1, and 3. How could you get this to break up some? Well, could we use our division, our synthetic division or something to break this up a bit? Okay. For example, we could do the -3. Okay. Let's see, this would actually be 3. Or, let's go ahead with the 1. Let's say something like that. That's easier to... We have a 7. We have a -21 on the x squared, a -7, and a 21 there. So we have 7. 1 times 7 is 7. Minus the 21 is going to be a -14. Times 1 is a -14. That's going to give us a -21. 1 times the -21 is going to give us a -21. Remainder of 0. So this breaks it down a little bit. We now have x minus 1 times 7x squared minus 14x minus 21. Does that make sense what I just did there? So I did division to factor out the x minus 1. Does that make sense to everybody? Now, this can be rewritten then as x minus 1 times 7 times x squared minus 2x minus 3. Does that make sense what I did there? Factored out the 7. The 7 can be brought forward. We have an x minus 1. Then this last portion, the x squared minus 2x minus 3, will factor into x minus 3 times x plus 1. Does that make sense how we did that? Part of the way we used division to clean it up a bit. And then once we got it down to a lower degree polynomial that we could handle by factoring, we went ahead and factored that. And what you now have is 7. Yep, there it is. They're not quite in the same order. X plus 1, got it. X minus 1, got it. X minus 3, got that as well. Are you okay with factoring something if you're given the roots? Okay. Use the graph to factor that. How can we use that graph to factor a polynomial? I mean, I can't take this polynomial, divide it into 2x cubed minus 4x squared. I can't do that, can I? So how am I going to use that for the division, for the factorization? What am I going to do with that graph? Suggestions? Okay, take a look here. Does that give us a 0? Yeah, that tells us x equals 1, or we're hoping it's x equals 1 and not 1.0362 something or other. Okay, this hopefully also gives us a 0, and we'll try it. X equals 3, and then this gives us a 0. x equals negative 2. So what we can do here is we can try our division. I'm going to do the 1. Why did I pick 1? It's easier to work with. I'm going to drop the 2 down. 1 times 2 is 2. Minus 4 plus 2 is a minus 2. 1 times that's going to be a minus 2. Minus 10 is a minus 12. 1 times that's going to be a minus 12. Plus 12 is 0. Now, it's good news that it came out to be 0. If the remainder is not 0, is it a factor? No. The only way it can be a factor is if you get a remainder of 0. Okay, so be careful. Well, what this gives us then is x minus 1 times 2x squared minus 2x minus 12. What would be a next step in the complete factorization of this? There are a couple ways you can go. What would help clean up that second factor? Could you factor out a 2? Yeah. And that would give us then, we have our x minus 1. Now, I'm going to go ahead and move the 2 up front. Come on. And what that's going to leave us with over here is an x squared minus x minus 6. Okay, so far? This is going to then give us 2. We have our x minus 1. Uh-oh, how does this factor? Do you see this becomes an x minus 3 times x plus 2? The x plus 2 gives us that value. The x minus 3 gives us that value. And then our x plus 1 gives us that. And whoa, we got it factored. Now, I have my factors in a different order than what they have down here. Is that a problem? No. It's fine either way. Okay. Does that make sense to everybody? One of the things that we've talked about already that they illustrate here, I was trying to lay some groundwork ahead of time, is if you have a factor, for example, x plus 1, that means you're going to divide by a negative 1. No big surprise there. But what we talked about earlier is if this remainder is 0, that tells you that the factor you are working with truly is a factor. So if it turns out to have a 0 in the lower right as the remainder, then whatever you're testing by dividing by really is a factor of that particular polynomial. Does that make sense? And when you factor out the x plus 1, which is what we did by dividing, you're now left with this 2x squared minus 4x minus 30, where the 2 on the x squared comes from there, the minus 4 from there, and the minus 30 from there. Okay. If you have zeros that have a higher order multiplicity, you're used to a multiplicity of 1. A multiplicity of 1 would look like x plus 5 times x minus 3 times x minus 7. Each of those zeros occurs one time, okay, which would then allow us to draw a graph where at negative 5 it crosses, at 3 it crosses, and at 7, it crosses. And it's going to do, hopefully, I'm going to ask Kelly to check my work. Does that look reasonable? If you have something with a multiplicity, okay, that's odd, you know it's going to cross. If it has a multiplicity that's even, it's going to touch that point and then back away from it. However, as the multiplicity increases, so what I'm going to look at is on this left-hand graph right there. As the multiplicity increases, okay, so is this x minus 3, which is the factor, and it right now has a multiplicity of 2. If we increase that multiplicity, okay, the higher the multiplicity, the more the graph levels out near that point. Which would mean that instead of coming down quite so steep, instead of coming down like this, it would come down more like this. As you increase the multiplicity, it's more likely to flatten out some as it gets close to that point of interest, that 0 point. Does that make sense? And that's true for either an even or an odd multiplicity. Okay, so where does that get us? Well, it gets us to this thing called the rational root test, and or rational zeros test. Roots, zeros, they mean the same thing. Okay. And the idea is, suppose we have some polynomial, y equals 4x to the third minus 7x squared plus 8x, let's say minus 6. Okay. If p over a is a rational number, then it's a 0. Now wait a minute, what's p over a? P is a factor of the constant term, so p comes from the constant, and q is a factor of whatever your leading coefficient is. Okay, so how do we apply that to this? Well, for our constant, what are the different possible factors of 6? Well, plus or minus 1 will work, won't it? Plus or minus 2, plus or minus 3, plus or minus 6. Those are all factors of 6, aren't they? Then for our lead coefficient, we want the factors of 4. Well, that's going to be plus or minus 1, plus or minus 2, plus or minus 4. Okay. Now what do? Well, we mix and match all the possibilities. P is the constant, Q is the lead, and what we're going to do is we're going to create a whole series of fractions by mixing and matching the P and the Q from the list up there. So we can do plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 1 over 4. What I did there was I took the 1 from the constant, okay, let me use the pointer. I took the 1 up there, and I'm using that as my numerator down at the bottom. Then for my denominators down here, I just selected the different possible factors of 4 and put them in there. Okay, so these are all possible roots. Possible, not guaranteed to be the actual deal. The next thing I could do then would be plus or minus 2 over 1, plus or minus 2 over 2. Now I don't have to use that one. Why don't I have to use 2 over 2? It's just 1. It's already accounted for. Okay. Plus or minus 2 over 4. Do we need that one? Nope. It's accounted for. So the good news is, even though it looked like we were going to pick up 3 more possibilities, we only really picked up 1. Then we're going to go to plus or minus 3 over 1, plus or minus 3 over 2, and plus or minus 3 over 4, and I'm going to check. Do any of these new numbers that we've just introduced pop up earlier? Nope. So those are all new possibilities. Then I'm going to go to the last factor, is 6. And that's going to give us plus or minus 6 over 1, plus or minus 6 over 2, plus or minus 6 over 4. Are any of those repeats? Yeah, the 6 over 2 is the 3, which is right there. The 6 over 4 is a repeat of 3 over 2. Okay, now, if you've got a TI-83 or 84, this is where life gets really easy, or a lot easier. What you can do is you put this function in for y1. And this is where we'll pick up next time. Okay? And then you evaluate every single one of these, and the ones that come up equaling 0 are factors. How many factors will there be total for this particular situation? A maximum, well, let's see, it's degree 3 polynomial, so that means a maximum of 3 factors. And one of them might have a multiplicity of 2, or might even have a multiplicity of 3. Who knows? We'll pick up here. Okay? You can finish off the homework in the section 4.3, which is the division. If you want to start trying some of this stuff in 4.4, just to get some of the homework done and out of the way, have at it. Friday's quiz, we'll talk some more about this and then throw section 4.4 in, and you can work in groups or something or other like that. Okay? Folks, I hope you have a terrific day, and I will see you all on Friday.